You have been tracking Atlas. You are aware it is the third entity from beyond our solar system to visit. You know it is enormous, moves at great speed, and exhibits peculiar characteristics. However, what you might not realize is what is slated to occur on October 29th. In slightly more than 4 weeks, Atlas will vanish behind the Sun, becoming invisible to every terrestrial telescope. And according to Avi Loeb, an astrophysicist at Harvard, this is not by chance. It represents a chance. The opportunity to harness the Sun's gravitational pull to propel itself into a perpetual orbit, thereby becoming permanently ensnared within our solar system. Now, this is where things become truly extraordinary. Within the last 48 hours, fresh data has emerged. Its mass, at a minimum of 33 billion tons, is vastly greater than anyone had previously conjectured. Its chemical composition defies all known scientific principles. And that emerald luminescence that has captured everyone's attention materialized at the precise instant it should have been physically impossible. We have just concluded our analysis of Lowe's comprehensive interview, the one where he meticulously details every single irregularity, every statistical improbability, and every conceivable reason why this phenomenon might not be what we are being led to believe. We are about to dissect precisely his assertions, the actual revelations contained within the data, and the ramifications that will unfold as Atlas disappears from view in 29 days. Because regardless of whether you perceive this as merely an unusual comet or something far more deliberate, one aspect is undeniable. October 29th marks the pivotal moment when everything could irrevocably change. It is the crucial window for maneuvering, the point of no return, and we will thoroughly examine precisely why Lowe advises you to take your holiday before that specific date. Let us delve into the details. But first, if you appreciate in-depth explorations of this nature, please activate the like button and subscribe. Furthermore, share in the comments section your current location, the local time, and the most peculiar incident you have ever experienced. Chapter 1. October 29th signifies a transformative event. Let us commence by examining what Avi Loeb actually articulated in this interview, as the manner in which he initiates his argument provides profound insight into his perspective. He does not begin with conjecture. He does not open with the hypothesis of extraterrestrial origin. He starts with a specific measurement, 20 kilometers. This was his initial estimated size of Atlas, derived from its luminosity upon its initial discovery, 20 kilometers in diameter. To provide context, this dimension surpasses that of Manhattan Island. It is double the size of the asteroid that impacted Earth 66 million years ago, leading to the extinction of the dinosaurs. This is an immense size for an object that purportedly originated from another star system and has been traversing the galaxy ever since. And this is where Lowe's intellect immediately gravitates towards statistical analysis. He states, "Observe, we possess a general understanding of the quantity of rocky material present in interstellar space. We can estimate this based on our observations of star-forming regions, our models of planetary formation, and the abundance of heavy elements dispersed throughout that expanse." He continues, "And when you perform the calculations, when you determine the frequency with which a celestial body of this magnitude is statistically likely to intersect with our inner solar system, you arrive at a figure. Once every 10,000 years. He reiterates, once every 10,000 years. And we have been systematically searching for interstellar objects for approximately a decade now, perhaps slightly longer if we account for the period preceding the development of technologies capable of precise identification. He concludes, a single decade of observation, and we encounter an object that should statistically manifest only once every 10 millennia. The probability of such an occurrence is, to put it mildly, highly unusual. However, Lowe ventures even further. He highlights the fact that we had already identified 2 prior interstellar objects before Atlas, Oumuamua in 2017 and Borisov in 2019. Both of these were relatively small. Oumuamua was approximately 100 meters in length, comparable to the size of a football field. Borisov was similarly sized, a few hundred meters across. These are considered normal dimensions for objects originating from another star system. The distribution of celestial bodies in space adheres to a discernible pattern. There are substantially more diminutive objects than their larger counterparts. This is a fundamental principle of physics. As planets form and star systems eject material into interstellar space, countless small fragments are generated for every larger mass. Consequently, statistically speaking, we should encounter an immense volume of small interstellar objects preceding the detection of a substantial one. Lowe calculates that we ought to have discovered around 100,000 interstellar objects comparable in size to Oumuamua before encountering something as massive as Atlas. 100,000, and we had only identified 2. Now, one could contend that our detection methodologies might be biased towards larger objects. It is conceivable that smaller entities are simply more challenging to discern, and Atlas presented itself first due to its considerable brightness and prominence. And that would be a valid argument, were it not for a single critical factor. Atlas was not anticipated to exhibit such luminosity at the distance at which it was initially observed. When Atlas was first detected on July 1, 2025, it was situated beyond Jupiter's orbital path, a considerable distance away where solar illumination is diminished and objects typically appear faint. Most comets at that proximity are virtually imperceptible. They remain frozen solid, inert, merely conglomerations of ice and rock drifting through the frigid void. They do not develop their characteristic coma, that luminous envelope of gas and dust, until they approach much closer to the Sun, typically within the orbit of Mars. Yet, Atlas was radiating light, not marginally, but with a brilliance sufficient for easy detection, a luminosity so pronounced that initial estimates posited it must be enormous to reflect such a magnitude of sunlight. It was akin to observing a street lamp illuminating the heart of the Antarctic wilderness. Such activity was not expected at that juncture. Loeb emphasizes this point in his discourse. He elaborates on how comets generally require proximity to the Sun, within approximately 5 astronomical units, which is 5 times the Earth-Sun distance, before solar radiation becomes sufficiently intense to initiate the sublimation of ice and the resultant outgassing that renders them visible. Jupiter is situated at a distance exceeding 5 astronomical units. Atlas was radiating light even from a greater distance than that, further than it logically should. This suggests an alternative explanation, one of the initial instances where the hypothesis of extraterrestrial technology emerges, unless its illumination was not derived from solar radiation at all, but rather generated internally. However, let us not anticipate events. We shall meticulously follow Loeb's line of reasoning, as this is precisely where the evidence begins to accumulate. This is where the coincidences start to interlock, creating a pattern that compels one to question whether coincidence is indeed the appropriate descriptor. The subsequent observation Loeb directs attention to is the trajectory, and this is where the argument for deliberate fine-tuning truly solidifies. When an interstellar object enters our solar system, it can originate from any direction and at any angle. There is no inherent reason for it to prioritize the plane in which our planets orbit. This represents the geometry of our solar system, not its own. An object originating from another star should arrive at a random inclination, a random orientation, entirely independent of our ecliptic plane. Yet, Atlas deviates from this expectation. Atlas arrives on a path that is aligned with the ecliptic plane to within a mere 5 degrees. 5 degrees. That is remarkably close to flat. It is almost perfectly synchronized with the orbital paths of Earth, Mars, Venus, and Jupiter, as well as all the inner planets. Loeb quantifies this statistical anomaly. He states that the random probability of this alignment occurring is 1 in 500. 1 in 500. While not an absolute impossibility, it is indeed rare. It is sufficiently uncommon to warrant significant attention. It is sufficiently unusual to provoke contemplation. But the remarkable circumstances continue to escalate. Atlas not only aligns with the plane, but its trajectory facilitates relatively close passes with multiple planets. Extremely close passes. On October 3rd, merely a few days from the present moment of this recording, Atlas will traverse within 29 million kilometers of Mars. This constitutes an intimate proximity in astronomical terms. It is close enough that NASA's Mars Reconnaissance Orbiter is scheduled to attempt imaging it using its HiRiser camera. And the celestial encounters do not cease there. Atlas also executes comparably close approaches to Venus and Jupiter, all 3 planets, each encounter occurring at precise points in their respective orbits, with the timing coincidentally aligning with Atlas's passage. Loeb has also meticulously calculated the probabilities associated with these events. He has determined the cumulative likelihood that an interstellar object, following a random trajectory, would pass as closely to Jupiter, Mars, and Venus as Atlas does, at the very moments when these planets are positioned favorably within their orbits. The calculated probability is 1 in 20,000. 1 in 20,000. Consider this for a moment. We are no longer discussing isolated coincidences. We are contemplating a series of improbable events, each stacked upon the last. The sheer size, the unexpected luminosity at a distance where such brilliance should be absent, the precise alignment with the ecliptic plane, and the close proximity to 3 distinct celestial bodies. Individually, each of these occurrences might be attributed to random chance. However, When considered collectively, Loeb draws a compelling analogy during the interview. He posits, one can argue that each individual event is merely a statistical anomaly. The trajectory is random, and it just so happens to be aligned. The close passes are a matter of luck, with the timing falling into place fortuitously. But at a certain point, when one repeatedly achieves a perfect score, the logical conclusion is to suspect that the dice might be manipulated. And then he presents the most significant revelation, the element that, if substantiated, would constitute the most compelling evidence for intentionality. Atlas reaches its closest point to the Sun, its perihelion, on October 29th. And on that specific date, Earth will be positioned diametrically opposite the Sun. Consequently, it will be entirely beyond our observational capabilities. Every telescope on Earth will have the Sun situated directly between us and Atlas. It will be in solar conjunction, completely obscured from our view. Loeb explains, this could be a deliberate action. This could represent the opportune moment to execute a maneuver. If one intended to utilize the Sun's gravitational influence to decelerate, to alter one's trajectory, to insert oneself into an orbit around the Sun without being detected, this would be the ideal juncture to do so, concealed behind the Sun, beyond sight. He refers to this as a reverse solar oath maneuver. Typically, spacecraft leverage the oath effect to augment their velocity. Propulsion is engaged when an object is moving at its maximum speed, in closest proximity to a substantial celestial body like the Sun, because even a minor application of thrust at such a point yields the most significant alteration in velocity. However, the principle can be applied in reverse. Propulsion can be engaged to decelerate, to dissipate velocity, thereby allowing gravitational forces to capture the object into an orbit. And if Atlas were to undertake this maneuver on October 29th, while concealed from our observation, it could effectively anchor itself within our solar system indefinitely. It would not simply traverse our system and depart, as a conventional interstellar object would. Instead, it would remain in orbit around the Sun, completing periodic circuits and lingering within our cosmic vicinity. Loeb points out that the timing of its arrival at perihelion, coupled with its concealed status from Earth at that precise moment, introduces an additional layer of improbability. If one were to marginally adjust Atlas's trajectory, shifting its arrival time by a few weeks earlier or later, the probability of it reaching perihelion precisely when Earth is on the opposite side of the Sun is exceedingly slim. While not impossible, it is highly unlikely. It is yet another confluence of events that aligns with remarkable precision. And it is at this juncture that Loeb transitions to discussing the implications. He states, consider this. If this is indeed extraterrestrial technology, then it is selecting the most advantageous moment to execute a significant action. The optimal point for a deceleration maneuver is at perihelion, when proximity to the Sun is maximized and its gravitational influence is at its peak. Furthermore, it is obscured from our observation by the Sun itself. This demonstrates not merely strategic acumen, but the kind of action one would undertake to avoid detection during course alterations. He is careful to present this as a potential scenario rather than an established fact. He employs phrases such as could be, and if it were technological, this would allow. He is delineating a hypothetical situation, exploring a scientific hypothesis, but the underlying implication is unequivocal. The circumstances are too perfectly orchestrated. The timing is too convenient. The trajectory is too precisely calibrated. And this represents only the initial phase of his argument. This pertains solely to orbital mechanics. He has yet to address the visual observations, the chemical anomalies, the phenomena documented by the Hubble and Webb telescopes, and numerous other observatories that have been tracking this object for the preceding 3 months. However, based solely on the trajectory analysis, it becomes evident why Loeb believes this warrants serious consideration, why he advocates for at least contemplating the possibility that we are not observing a random cosmic artifact, but rather something imbued with deliberate intent. Chapter 2. Larger than Manhattan. Let us delve deeper into the issue of its size, as it is not solely about Atlas being large, but about the implications of that size for our understanding of interstellar object behavior, their prevalence, and what we should have encountered prior to detecting an object of such magnitude. When Loeb discusses the 20-kilometer estimate in his interview, he is referencing the initial calculations based on its luminosity. Astronomers determine the size of a distant object through a relatively straightforward principle. They measure the amount of sunlight it reflects, then estimate the reflectivity of its surface, known as albedo. From this, they can extrapolate its size. For Atlas, these preliminary calculations consistently yielded the same result, 20 kilometers. Loeb immediately recognized this as problematic. Not because a 20-kilometer cometary body is inherently impossible, as we have observed comets of such dimensions within our own solar system. The issue lies in the fact that encountering such a large object as an interstellar visitor so early in our observational campaign defies the expected distribution patterns. Here is the fundamental principle regarding cosmic debris. Whether we are referring to asteroids, comets, or interstellar rocks, their distribution follows a power law relationship. This implies that for every larger object, there exists an exponentially greater number of smaller objects. If there is one rock measuring 10 kilometers in diameter, there might be 100 rocks measuring 1 kilometer in diameter, 10,000 rocks measuring 100 meters in diameter, and 1 million rocks measuring 10 meters in diameter. The quantity escalates dramatically as the size decreases. This pattern is ubiquitous in nature. It governs the distribution of impact craters on the moon, the magnitude of earthquakes, and even the population distribution of cities. Large entities are uncommon, while small entities are abundant. The universe generates far fewer mountains than pebbles. Consequently, when Loeb applied this principle to interstellar objects, he anticipated this distribution pattern to hold true. And if it does, if the distribution aligns with the same power law observed universally, then we should be inundated with small interstellar visitors before ever detecting a substantial one. We ought to have cataloged thousands, perhaps tens of thousands, of objects similar in size to oumuamua, those entities measuring approximately 100 meters, before experiencing the fortune of observing something as massive as a 20-kilometer comet. Yet, we had not. We had identified precisely two, oumuamua and Borisov, both relatively small, both within the 100 to few hundred meter range. And then, unexpectedly, Atlas appears, and it is potentially 100 times larger in diameter, signifying thousands of times greater volume. Loeb articulates this point in the interview. He states, "Given the limited availability of heavy elements in interstellar space, we should have discovered on the order of 100,000 interstellar objects the size of oumuamua before encountering Atlas. 100,000. And we had only previously detected 2 interstellar objects. Now, the interpretation of this discrepancy can diverge. One perspective suggests that our detection methods are simply inadequate for discerning smaller objects, and we are primarily identifying the larger, more luminous entities. This is a plausible explanation, as telescopes have inherent limitations, and small, dim objects are difficult to observe. Alternatively, it is possible that the initial size assessment was erroneous. Perhaps Atlas is not actually 20 kilometers in diameter. It is conceivable that its observed brightness originated from a source other than a colossal solid nucleus reflecting sunlight. It might have been enveloped by an extensive cloud of gas and dust, thereby appearing larger and brighter than its actual size. As it happens, this latter possibility aligns more closely with our current understanding. More recent observations, particularly those conducted by the Hubble Space Telescope, have significantly refined the size estimate. As of late August, data from Hubble indicated that the maximum estimated diameter of Atlas is approximately 5.6 kilometers. While still substantial, definitively larger than previous interstellar visitors, it is not 20 kilometers, nor Manhattan-sized. 5.6 kilometers is a more reasonable dimension. It remains an unusual characteristic, still larger than what we would anticipate at this early stage of our investigation, but it falls within the realm of possibility for a natural comet. It does not completely disrupt the statistical model in the same manner that a 20-kilometer object would. However, this is where the situation becomes compelling once again. Because, just this week, within the last 48 hours, new data has surfaced that introduces further complexity to the scenario. Loeb and his research colleagues have published a novel analysis, not yet subjected to peer review, that examines Atlas's trajectory with extraordinary precision. They aggregated data from 227 observatories globally, comprising over 4,000 individual observations spanning several months. Through this extensive data collection, they meticulously measured the precise movement of Atlas through space. And their findings indicate that Atlas exhibits virtually no non-gravitational acceleration. Let me elucidate the significance of this observation. As a comet approaches the sun and begins to heat up, the ice on its surface undergoes sublimation, transforming directly from a solid to a gaseous state. This gas is then expelled into space, creating jets. When gas is ejected from one side of a comet, it functions analogously to a miniature rocket engine, imparting a subtle push to the comet and altering its trajectory in ways that pure gravitational forces alone would not predict. Astronomers term this phenomenon non-gravitational acceleration, and it is a definitive characteristic of active comets. The presence of non-gravitational acceleration can be ascertained by tracking a comet's position over time and comparing it to its predicted path based solely on gravitational influence. Any deviation, whether ahead or behind the predicted gravitational position, indicates that outgassing is exerting a directional force. Atlas, according to this recent analysis, displays almost no such effect. Its observed position aligns with a purely gravitational trajectory within exceptionally narrow margins. The upper limit for its non-gravitational acceleration is less than 15 meters per day squared. This is an infinitesimally small value, considerably less than what would be expected from a comet actively undergoing outgassing. And we have evidence that Atlas is indeed outgassing. The Webb Space Telescope observed it on August 6th and detected the release of gas from its surface. The rate of mass loss is approximately 150 kilograms per second. This is a substantial quantity of material, sufficient to generate measurable thrust and consequently exert a detectable influence on the comet's trajectory. So, why is it not exhibiting this influence? Why is Atlas moving as if only subject to gravitational forces when it is demonstrably expelling gas into space? Loeb's explanation is straightforward. Its mass is too great. If Atlas possesses sufficient mass, if it is sufficiently heavy, then the thrust generated by its outgassing will have a negligible impact. It is akin to attempting to propel an ocean liner with a leaf blower. The force is present, but the immense mass renders the resulting acceleration imperceptible. Consequently, they perform the necessary calculations. Considering the observed rate of outgassing and the absence of detectable non-gravitational acceleration, what is the minimum mass Atlas could possess? Their calculation yielded a result of 33 billion tons. 33 billion tons. This represents the lower bound. Atlas must weigh at least this amount. Otherwise, we would observe it being perturbed by its own gaseous emissions. And if its weight is 33 billion tons, and we assume it is composed of rock and ice with a density comparable to other comets, we can calculate a minimum diameter, which emerges as greater than 5 kilometers, potentially significantly more depending on its actual density. Thus, we are confronted once again with a substantial object, not 20 kilometers, probably not, but undeniably at the larger end of the spectrum. It is definitively more massive than any other interstellar object we have previously observed. Loeb points out that this renders Atlas 3 to 5 orders of magnitude more massive than oumuamua or Borisov. This translates to a factor of 1,000 to 100,000 times heavier. And this brings us back to the original statistical conundrum. If Atlas is indeed this massive, its detection so early in our survey of interstellar objects constitutes, in Loeb's words, a significant anomaly. It is analogous to flipping a coin and obtaining heads 1,000 consecutive times. Is it technically possible? Yes. Is it probable? No. However, there exists an alternative interpretation for the 33 billion ton figure, an alternative possibility that Loeb alludes to without fully committing to in the interview. What if Atlas is not a solid mass? What if it is hollow? What if it comprises a shell, a constructed entity, something possessing considerable volume but a low mass per unit of volume? If one were to endeavor to construct a spacecraft capable of interstellar travel, one would not fabricate it from solid metal. That would entail an immense quantity of mass, a prohibitively high expenditure of energy for acceleration and deceleration. The construction would involve a hollow outer casing, a slender external framework with substantial unoccupied internal volume. This mirrors our terrestrial shipbuilding methods and aligns with natural structural designs. Biological skeletons are hollow, as are plant stems. This methodology optimizes strength while minimizing weight. A hollow structure spanning 10, 15, or even 20 kilometers in diameter, if sufficiently robust, could easily attain a mass of 33 billion tons. Externally, it would present as a monolithic entity, reflecting solar radiation much like a sizable geological formation. However, its measured mass would betray a stark divergence from that of a comparable solid mass. While Loeb does not explicitly articulate this in the interview, he alludes to it metaphorically. He suggests we should avoid superficial judgments, positing that the detected surface composition of Atlas, the carbon dioxide and water ice, might simply be accretion from its interstellar transit, akin to frost accumulating on a windshield. Yet, the implication is undeniable. If one entertains the hypothesis of Atlas being an artificial construct, the 33 billion ton mass transforms from an anomaly into a significant data point. Its considerable weight is less than that of a solid celestial body of equivalent dimensions. The mass is sufficient to counteract the thrust from outgassing. yet light enough to suggest fabrication rather than natural genesis. This is the juncture where Loeb's reasoning transcends isolated observations, coalescing into a network of interconnected peculiarities. The sheer magnitude is unconventional. Its trajectory is irregular. The timing is peculiar. The absence of non-gravitational acceleration, given the observed outgassing, is anomalous. Individually, none of these factors provide definitive proof. Nevertheless, their confluence creates an impression of an object that defies conventional classification. Loeb acknowledges this discrepancy, stating that the most probable explanation remains that Atlas is a completely natural interstellar object, likely a comet. He refrains from asserting certainty or definitively proclaiming alien technology, but maintains that current data does not preclude such a possibility. In his estimation, this uncertainty warrants intensified scrutiny, necessitating the deployment of every available observational instrument, telescopes, spacecraft, and analytical tools, for its study while it remains within reach. The transient nature of interstellar objects is crucial. They traverse our solar system and then recede into the void, becoming permanently inaccessible. If Atlas is indeed a comet, its study will yield valuable insights into extraterrestrial cometary phenomena. However, if it represents something else, even a mere 1% probability, foregoing a thorough investigation would constitute a profound error in human judgment. Thus, the size argument, the mass conundrum, presents Atlas as a substantial interstellar visitor, potentially exceeding expected dimensions for an object encountered this early. Its weight, at a minimum of 33 billion tons, though less than a solid mass of similar scale, coupled with its orbital characteristics and temporal placement, renders it sufficiently enigmatic to prompt Loeb's persistent inquiry. What if? Chapter 3. A precisely calibrated trajectory. Let us now examine the celestial path of this object through our solar system, as this is where the argument for deliberate calibration gains considerable traction. In his interview, Loeb dissects the trajectory analysis, not merely highlighting isolated coincidences, but meticulously detailing a sequence of improbable events. Each element of orbital mechanics, individually plausible yet unlikely, collectively suggests intentional design. The alignment with the ecliptic plane is the first such observation. Our solar system exhibits a degree of flatness, with the 8 principal planets orbiting the Sun within a similar plane, often visualized as a disk with the Sun at its center. This plane is termed the ecliptic, serving as a foundational organizational principle of our immediate cosmic environment. All indigenous celestial bodies, formed from the primordial nebular disk billions of years ago, adhere to this geometric framework. Asteroids predominantly orbit near the ecliptic. Comets originating from the Kuiper belt, while exhibiting inclination, still maintain a loose association with it. Interstellar objects, however, are theoretically unconstrained by these local dynamics. Originating from diverse stellar systems, they possess their own orbital planes, orientations, and rotational axes. Consequently, an object arriving from beyond our solar system should manifest from a random direction at an arbitrary angle. The probability of its trajectory closely approximating our ecliptic plane by mere chance is exceedingly low, though not impossible. Loeb quantifies this probability at approximately 1 in 500, or a mere 0.2%. If one were to examine 500 randomly encountered interstellar objects, one might statistically expect one to exhibit such a degree of alignment through sheer fortuity. Atlas, however, represents only the 3rd such object ever detected. This already places us in a scenario where the odds are roughly 500 to 3 in favor of non-randomness, a statistically improbable but not entirely inconceivable outcome. The subsequent factor is the series of close planetary encounters. Atlas does not simply traverse our solar system at an arbitrary distance from its planets. It passes in proximity to 3 of them: Mars, Venus, and Jupiter. Furthermore, these close approaches are not merely spatial but temporal. It arrives at the orbital vicinity of each planet precisely when that planet is in a corresponding position. Consider the complexity of this synchronization. The planets are in constant motion. Mars completes an orbit in approximately 687 days, Venus in 225 days, and Jupiter in 12 years. Each occupies a distinct orbital radius and travels at a different velocity, occupying specific spatial locations only at particular moments. For an interstellar object to achieve proximity to all 3 planets during its passage, the temporal alignment must be exceptionally precise. Loeb has performed calculations to assess this probability. He analyzed Atlas's trajectory, determining the minimum distances it achieves relative to each planet's orbital path, factoring in their actual positions at the time of Atlas's transit. The combined probability of all three close encounters occurring by chance, given a random arrival time and trajectory, is approximately 1 in 20,000. This shifts the odds dramatically from the previous 500 to 1 scenario, now involving tens of thousands to 1. This calculation pertains solely to the planetary encounters, excluding the ecliptic alignment, which represents a distinct statistical consideration. On October 3rd, a mere few days hence, Atlas will pass within approximately 29 million kilometers of Mars. In cosmic terms, this constitutes a near miss. The proximity is sufficient for NASA to plan utilizing the high-resolution imaging science experiment, HiRISE, camera aboard the Mars Reconnaissance Orbiter to directly image Atlas. HiRISE is engineered for capturing Martian surface imagery at exceptionally high resolution, capable of discerning individual boulders and rover tracks. Directing it towards Atlas is anticipated to provide the most detailed visual representation to date of this object, potentially differentiating its nucleus from the surrounding coma and dust cloud. However, the truly compelling aspect lies in the minimum orbit intersection distance. The closest Atlas's projected path comes to Mars' entire orbital path, which is a mere 2.7 million kilometers. This is an astonishingly small gap from an astronomical perspective. A slight deviation in Atlas's orbit, an earlier or later arrival, or a trajectory tilted by a mere few degrees, could have resulted in an even closer approach, potentially intersecting Mars' orbit precisely when Mars was present. Loeb highlights this point, asserting that this fine-tuning, this close proximity to Mars coupled with the encounters with Venus and Jupiter, suggests a trajectory that is either extraordinarily fortuitous or meticulously orchestrated. If intentionality is present, the October 3rd Mars encounter might transcend a mere flyby, representing a strategic opportunity. An opportunity for what? This is where speculation intensifies. Loeb posits that if Atlas were an artificial construct, perhaps a spacecraft or probe, then a close passage by Mars would provide an opportune moment for deployment. This could involve a smaller secondary probe, a lander, or a scout. Such an object could be released, execute a minor course correction, and intercept Mars while the primary vehicle continues its trajectory toward the Sun. He even quantifies the necessary parameters. If Atlas were to release a precursor probe traveling ahead and laterally by approximately 30 million kilometers, that probe could reach Mars around October 3rd, coinciding with Atlas's closest approach. The required ejection velocity would be modest, a few kilometers per second, easily achievable with even minimal propulsion. Critically, from Earth, such a deployment would remain undetected, as our current observational capabilities are insufficient to track such diminutive objects at that range. Our telescopes can resolve objects down to approximately 10 to 20 meters at Jupiter's distance, but not significantly smaller, and certainly not if their design incorporates stealth. Is there any evidence to suggest Atlas has deployed any such auxiliary object? No, there is no such evidence. This remains purely speculative. However, Loeb's contention is that such possibilities should be actively investigated. Vigilant observation of Mars during and after the October 3rd encounter is imperative. Should any anomalies appear in Martian orbit, or if any of the existing spacecraft orbiting Mars detect unusual phenomena, such findings would carry significant implications. Furthermore, there is the Venusian encounter. Atlas will also approach Venus relatively closely, though not as intimately as Mars. Jupiter, situated further out in its orbit, will also be subject to an encounter, albeit at a greater distance. The confluence of all three planetary approaches during a single transit through the inner solar system is, again, statistically improbable, though not impossible. However, the precise timing of perihelion, the point of closest approach to the Sun, is where Loeb focuses his primary attention. This is because perihelion is scheduled for October 29th, a date on which Earth will be positioned diametrically opposite the Sun, placing Atlas in solar conjunction. Consequently, direct observation will be impossible. All ground-based telescopes will have the Sun directly obstructing their view. Even space-based observatories, unaffected by daylight, will encounter significant challenges due to the Sun's overwhelming glare, which obliterates faint objects in its vicinity. Loeb refers to this as a concealed vantage point. He argues that if one were to design a trajectory that facilitated an unobserved maneuver, this would be the ideal scenario. Perihelion represents the optimal location for a braking maneuver due to the Sun's immense gravitational influence at that proximity. The Oberth effect, whereby orbital mechanics amplify thrust when traversing at high velocity near a massive object, operates in reverse here. By firing engines to decelerate and reduce velocity, the sun's gravity assists in capturing the object into an orbit. If Atlas's objective were to remain in orbit, to transition from a hyperbolic escape trajectory to an elliptical bound orbit, October 29th would be the opportune moment, and the event would occur undetected. We would only become aware of this transition retrospectively, upon Atlas's reappearance from behind the sun in late November or early December, when its recalculated trajectory reveals it is no longer on an escape path. Do we have any indication that Atlas possesses propulsion systems or is capable of course corrections? We have no such evidence. There is no discernible sign of propulsion, no thermal signature, no exhaust plume, nothing to suggest the operation of a rocket motor. However, it is reasonable to assume that an advanced civilization constructing interstellar probes would not employ conventional chemical rockets that emit visible combustion products. Instead, they would likely utilize more sophisticated and efficient propulsion methods, such as ion drives, magnetic sails, or technologies yet to be conceived. The crucial point is that a technological artifact does not necessarily manifest as a science fiction depiction of a spacecraft, complete with glowing engines and navigation lights. It could resemble a celestial body, be covered in ice and dust for insulation and camouflage, and execute subtle trajectory adjustments that would only be detected through exceptionally meticulous observation. Loeb corroborates this viewpoint in the interview, emphasizing the necessity of closely monitoring Atlas during its perihelion passage. He advocates for the utilization of every available spacecraft and probe within the inner solar system to track its movement with the utmost precision. The European Space Agency's Jupiter Icy Moons Explorer (JUICE) spacecraft, currently en route to Jupiter, is expected to provide a valuable observation of Atlas in November. NASA's Juno probe, already in orbit around Jupiter, may also be capable of observing it later. Mars orbiters will maintain watch in early October. We should direct all available resources towards this object to ensure no critical observations are missed. If Atlas does execute a maneuver on October 29th, slowing its velocity and achieving orbital capture, the implications would be profound. It would signify the presence of a visitor that is not merely transiting but intending to remain, establishing a presence within our solar system. We would then have approximately 6 weeks, from its emergence from solar conjunction in late November until its closest approach to Earth in late December, to ascertain its nature and intent. Loeb carefully frames this scenario as having a low probability of occurrence. He reiterates that the most likely outcome remains that Atlas is a natural comet destined to pass through and depart, mirroring the behavior of all previously observed interstellar objects. Nevertheless, he contends that this possibility, however remote, warrants serious consideration, as the cost of misjudgment, of overlooking a genuine technological visitor due to premature dismissal, far outweighs the expense of thorough investigation, even if the ultimate finding is a natural comet. This, in essence, constitutes the core of his argument. It is not an assertion that Atlas is unequivocally alien technology, but rather that the extant data does not definitively preclude such a conclusion. Furthermore, its trajectory exhibits sufficient peculiarity to necessitate exceptionally vigilant observation. The alignment with the ecliptic, the planetary flybys, and the meticulously timed perihelion all contribute to a portrayal of an object that is either extraordinarily fortunate or deliberately guided. Loeb employs a gambling analogy to illustrate his point, entering a casino and witnessing someone roll double sixes 10 consecutive times. While the odds are approximately 1 in 60 million, such an occurrence is statistically possible. However, witnessing such a streak would undoubtedly prompt a closer examination of the dice, an investigation into potential irregularities. This is precisely the approach he advocates. Let us examine the dice. Let us investigate the possibility of something unusual occurring. The trajectory of Atlas, its precisely calibrated path through our solar system, represents a sequence of events where the dice consistently yield sixes. Loeb's persistent message is that we must, at the very least, entertain the notion that the game might not be entirely random. Chapter 4. No tail, just headlights. We must now address the visual characteristics of Atlas, as these observations present a discrepancy with our expectations for a typical comet. This is also where Loeb makes one of his most striking pronouncements during the interview, the assertion regarding headlights. Comets, according to Loeb, are readily identifiable, much like zebras are recognized by their stripes. Their signature feature is their tail. As they approach the sun and undergo heating, the surface ice undergoes sublimation, transitioning directly from solid to gas. This process generates a luminous envelope of gas and dust surrounding the nucleus, known as a coma, and a tail that streams away from the comet, propelled by solar wind and radiation pressure. The tail consistently points away from the sun, irrespective of the comet's direction of travel. Its orientation is dictated by solar radiation and the solar wind, causing it to stream outward from the sun, akin to hair being blown by a breeze. This characteristic allows for immediate comet identification, locate the diffuse object, observe the tail's direction, and the sun's relative position becomes apparent. However, when the Hubble Space Telescope captured images of Atlas on July 21st, something appeared anomalous. Hubble recorded a teardrop-shaped cocoon of dust emanating from the nucleus, with a faint suggestion of a tail. Yet, its orientation was irregular. Instead of a clearly defined tail extending away from the sun, there was an illumination directed towards the sun, a forward-facing glow, as if the comet possessed headlights rather than a tail. It is crucial to exercise caution when interpreting telescopic imagery. Astronomical observation is inherently challenging. Photographing an object moving at interstellar velocities millions of kilometers distant necessitates specific exposure times. The object traverses distance during the exposure, potentially resulting in motion-induced smearing effects, creating a light trail in the direction of travel. If this direction happens to be towards the sun, it can create the illusion of a forward-facing illumination, even if it is merely a consequence of motion blur. NASA scientists promptly addressed this concern, suggesting that the apparent extension towards the sun in the Hubble image was likely an artifact of the imaging process. They explained that the comet's acceleration towards the sun, coupled with Hubble's tracking during the exposure, could cause background stars to streak, potentially generating a false impression of a forward-pointing tail. However, Loeb remained unconvinced. He was a co-author on a research paper that explored the possibility of Atlas being an alien artifact, citing this peculiar forward glow as one piece of evidence. Their argument posited that while motion blur might account for some of the observed phenomenon, the intensity and structure of the extension did not entirely align with what would be expected from pure motion blur alone. Subsequently, in late August, a significant development occurred. The Gemini South Telescope in Chile obtained new images of Atlas. This time, a distinct tail was visible, a faint appendage streaming away from the sun precisely as anticipated. By late August, Atlas had exhibited cometary behavior that appeared entirely normal. The scientists analyzing these images concluded that their initial suspicions were confirmed. Atlas is indeed a comet, actively outgassing and producing a coma and a tail. Case closed, according to their assessment. However, Loeb points out the peculiar timing of these events. For the first month and a half following its discovery, Atlas presented ambiguous visual characteristics: the forward glow, the absence of a distinct tail, and an unusual brightness for an object situated so far from the sun. Then, precisely as it traversed Mars's orbital path and solar heating intensified significantly, it began to exhibit behavior consistent with a normal comet. He uses a literary analogy in the interview. We should not judge a book by its cover. The presence of a cometary tail now does not definitively reveal what lies beneath. The surface could be coated with ice and dust accumulated during its interstellar journey, essentially, frost on the windshield. As this frost sublimates under solar influence, it would produce the exact type of tail expected from a comet, irrespective of the object's intrinsic composition. This is, admittedly, speculative. There is no direct evidence to suggest that Atlas possesses a composition beneath its surface that differs from that of a natural object. However, the argument is that visual appearance alone is not conclusive. A technological object traversing space for millennia would inevitably accumulate debris, interstellar gas, ice particles, cosmic dust. All of this material would adhere to its surface and freeze. By the time it entered a new star system, it would present an external appearance indistinguishable from a comet, even if its internal nature were entirely artificial. Furthermore, there is the enigmatic green luminescence. This is one of the most recent observations and presents a genuine puzzle, even to scientists who are firmly convinced of Atlas's natural origin. On September 7th, during a total lunar eclipse, two astrophotographers in Namibia captured images of Atlas under exceptionally dark skies. The eclipse rendered the moon entirely invisible, eliminating a primary source of light pollution, thereby enabling deep exposure photography of the comet. The captured imagery was striking. Atlas glowed with a vivid, unmistakable green hue. Green comets are not unprecedented. They have been observed previously. This coloration is typically attributed to diatomic carbon, a molecule composed of two bonded carbon atoms. When subjected to ultraviolet radiation from the sun, diatomic carbon fluoresces, emitting visible light within the green spectrum. This phenomenon operates on the same principle as a fluorescent light bulb. Energy is absorbed at one wavelength and re-emitted as light at another. A luminous green haze surrounding a celestial body typically indicates the presence of diatomic carbon within its coma. This substance is generated through the vaporization of organic compounds on the object's surface. Ordinarily, this phenomenon is unremarkable and expected. However, prior spectroscopic analyses of Atlas, conducted just 1 month before, in early August, revealed a scarcity of diatomic carbon. In fact, researchers at the Kitt Peak Observatory in Arizona determined that Atlas exhibited remarkably low levels of carbon chains, positioning it among the most depleted comets known. The molecules responsible for generating green fluorescence were present in unusually small quantities. Consequently, the question arises, how did it acquire its green hue in September? Where did the diatomic carbon originate? One plausible theory suggests the carbon was always present, simply concealed beneath the surface. As Atlas drew nearer to the sun, intensifying its heat, deeper ice layers melted, exposing fresh material richer in carbon compounds. This green glow might represent the visible manifestation of previously inaccessible interior ice. Another hypothesis, put forth by Loeb in a blog post following the release of the green imagery, posits that the color may not stem from diatomic carbon at all, but rather from cyanide. The Very Large Telescope in Chile detected a significant surge in cyanide production from Atlas in late August, which escalated dramatically as the comet approached the sun. Under specific conditions, cyanide can also produce a greenish luminescence. If its concentration reached sufficient levels, it could account for the vibrant color observed during the eclipse. Nevertheless, a third, far more speculative possibility warrants mention due to its connection to a broader pattern of anomalies. Could the green radiance signify a form of activation? Perhaps Atlas, irrespective of its true nature, crossed a threshold of solar heating that initiated a shift in its behavior. While Loeb does not explicitly state this in his interview, the implication is present. In his more recent writings, he emphasizes the suddenness of the color change, describing it as a threshold effect rather than a gradual transition. It was as if one moment there was no green, and the next, a vivid green appeared, akin to flipping a switch. If Atlas were a piece of dormant technology, having journeyed through the frigid expanse of interstellar space for millennia, it would necessitate a mechanism for activation upon entering a new star system. Temperature would serve as a logical trigger. As it approached the sun and its surface temperature increased, internal systems could power on. Instruments could activate, and this activation might produce byproducts such as heat, light, or chemical emissions, which we would interpret as typical cometary outgassing. This remains speculative, lacking definitive evidence, but it aligns with the pattern Loeb consistently highlights. Atlas behaves remarkably like a comet, yet not entirely. It possesses most expected characteristics, but with peculiar deviations, a tail that developed late, a forward glow that should not be present, and a color transformation inconsistent with spectroscopic data. While each individual anomaly might have a natural explanation, their collective presence paints a picture of something striving to resemble a comet but falling short. Furthermore, consider its chemical composition. The James Webb Space Telescope, on August 6, observed Atlas and analyzed the gas in its coma using spectroscopy, revealing an unusual finding. The ratio of carbon dioxide to water ice stood at 8:1. 8:1. This is among the highest ratios ever recorded for any comet, natural or otherwise. Most comets in our solar system exhibit a much greater abundance of water ice compared to carbon dioxide ice. Water is ubiquitous, found on every icy celestial body we have studied, from comets to Jupiter's moons to Saturn's rings, predominantly composed of water ice with trace amounts of other compounds. Atlas, however, presents the opposite scenario, dominated by carbon dioxide with a minimal quantity of water. What could explain this? One possibility is that Atlas originated in a frigid region of its home star system, far from its star, where carbon dioxide ice remains stable while water ice sublimates over billions of years. It could be genuinely ancient, predating our solar system, originating from a star that formed when the galaxy was younger and possessed different chemical compositions. Another explanation is that the carbon dioxide is a recent acquisition, forming as frost on the surface during Atlas's journey through interstellar space. Interstellar gas clouds contain carbon dioxide. If Atlas traversed such a cloud, molecules could condense on its frigid surface, accumulating a layer of CO2 ice over time. Alternatively, and this aligns with Loeb's argument, The CO2 could serve as a protective coating, a deliberate layer designed to insulate the object and regulate its temperature during interstellar travel. Carbon dioxide ice possesses distinct thermal properties compared to water ice. It vaporizes at different temperatures, reflects light differently, and offers specific shielding against radiation. An engineered probe designed for interstellar survival might incorporate CO2 as part of its thermal management system. This hypothesis, while highly speculative, is not physically implausible. We know that carbon dioxide ice behaves differently from water ice, can form stable deposits under suitable conditions, and that any object traversing space for millions of years would require protection from radiation, micrometeoroids, and extreme temperatures. Loeb consistently emphasizes the importance of avoiding assumptions, of not concluding that surface composition reveals everything about an object's interior. The 8-to-1 ratio is peculiar and warrants investigation, but it neither confirms Atlas's natural origin nor its artificial nature. It is simply another data point within a growing collection of discrepancies from the standard model. Chapter 5. Is it alien technology? Let us directly address the question Loeb raises in his paper and explores throughout the interview. Is Comet Atlas alien technology? Not could it be or might it be, but what would be required to definitively conclude that it is? This is where Loeb's approach becomes particularly insightful, as he refrains from merely presenting outlandish speculation. Instead, he endeavors to establish a framework, a methodology, a means of contemplating interstellar objects that does not automatically default to natural explanations, nor prematurely leaps to conclusions of alien origin without supporting evidence. In the interview, Loeb discusses what he terms the low scale, a rating system from 0 to 10 designed to classify interstellar objects based on their likelihood of being technological rather than natural. A score of 0 would represent an object exhibiting all characteristics of a typical comet or asteroid: a tail, predictable outgassing, a trajectory consistent with gravitational and rocket effects, and a standard composition, presenting nothing unusual or noteworthy. A score of 10 would indicate an object definitively identified as technological, maneuvering in ways unexplainable by natural forces, transmitting signals, displaying artificial structures in high-resolution imagery, emitting heat inconsistent with solar illumination, thereby suggesting an internal power source, or exhibiting behavior that unequivocally points to intelligence, leaving no room for doubt. Everything in between represents a gradient. An object displaying 1 or 2 anomalies might receive a rating of 3 or 4. An object with multiple unexplained features and accumulating statistical improbabilities could be rated a 6 or 7. The underlying principle is that as we encounter more interstellar visitors in the coming years, and we will, with the Vera C. Rubin Observatory expected to detect one every few months once fully operational, a consistent evaluation method, a triage system, is imperative. This system will help us identify which objects merit intense scrutiny and which are clearly merely passing space rocks. Loeb proposes that any object scoring above 5 on this scale should necessitate an international response. This response should not involve panic or military mobilization, but rather a coordinated scientific endeavor. We should leverage every available telescope, spacecraft, and observational tool for its study, pooling data internationally, because, as Loeb observes, extraterrestrials are indifferent to our terrestrial borders or national jurisdictions. An interstellar visitor is a challenge for all of humanity, demanding a global response. He further suggests the establishment of an organization, an international body specifically mandated to monitor interstellar objects and determine appropriate responses to any exhibiting technological signatures. Currently, such an entity does not exist. We have NASA, ESA, and various national space agencies that track near-Earth objects and monitor for asteroid impacts, but no unified protocol exists for handling the detection of an interstellar probe. Loeb argues for the necessity of such a protocol, emphasizing the brevity of our observational window. Interstellar objects travel at high velocities. By the time we detect them, they are often deep within the solar system, affording us only weeks or months for study before their departure. Wasting this precious time debating jurisdiction or the validity of investigation would mean missing the opportunity entirely. He draws parallels to other existential risks. We express concern regarding artificial intelligence, leading to conferences, research institutions, and government task forces dedicated to ensuring AI development does not inadvertently pose a threat to humanity. We are concerned about climate change, prompting international agreements, treaties, and summits for coordinated national responses. We even worry about asteroid impacts, with NASA maintaining a planetary defense program focused on tracking potentially hazardous objects and devising deflection strategies. Yet, for alien technology, there is no organization, no protocol, no plan. Loeb finds this perplexing. He contends that even if the probability of an interstellar object being technological is low, perhaps only 1%, the potential consequences are so significant that preparedness is essential. Unlike a radio signal from a distant star, which affords ample time for deliberation and planning, a visitor within our immediate vicinity demands swift action. So, where does Atlas fit on the Loeb scale? He does not provide an exact number in the interview, but by interpreting his remarks, it likely falls somewhere around a 5 or 6. It is not definitively technological, but it is anomalous enough to warrant serious attention. Its trajectory is unusual, its mass exceeds expectations, its visual characteristics are peculiar, and its chemistry is anomalous. While each individual feature might possess a natural explanation, collectively, they elevate Atlas into a category that cannot be dismissed as naturally occurring. Loeb's argument is not that Atlas is unequivocally an alien spacecraft, but rather that it is sufficiently peculiar to warrant close observation and an openness to the possibility of its non-natural origin. To prematurely dismiss it and overlook a genuine technological visitor would be a tragedy of historical magnitude. Loeb also speculates, venturing into more unsettling territory, that if Atlas is indeed technological, it might not be benevolent. He references the dark forest hypothesis, a concept from science fiction suggesting that the universe teems with intelligent civilizations, all maintaining silence due to the inherent danger of revealing their presence. If the intentions of another species are unknown and their potential hostility cannot be ruled out, the safest course of action is to remain concealed, to act as the predator rather than the prey. Within this paradigm, an interstellar probe entering a star system could be a reconnaissance mission, a scout gathering intelligence before a larger force arrives. Or it could be the vanguard of an attack, designed to disable defenses or deploy weapons before the target is even aware of the threat. Loeb carefully frames this as a thought experiment, not a prediction, stating in the interview that Atlas could either save us or destroy us, and we should be prepared for both eventualities. However, the underlying point is serious. If we detect something technological, we cannot assume it is benign. We must assess its capabilities, trajectory, and potential threat level, and we must do so rapidly while it remains distant enough for us to have options. What options would we realistically have? Honestly, very few. If Atlas is a spacecraft and has already entered the inner solar system, our capacity to intercept it would be minimal. We possess no weaponry capable of destroying a 20-kilometer object, nor spacecraft fast enough to intercept it at its current velocity. Our most viable recourse would be communication, attempting to transmit a message to establish contact, hoping that its creators are amenable to dialogue. Loeb suggests that if Atlas proves to be technological, one of our initial actions should be to transmit a simple message. Hello. Welcome to our neighborhood. We come in peace. This would be a standard first contact protocol, followed by observation to see if there is a response or any change in the object's behavior indicating it received and understood the message. However, all of this presupposes our ability to recognize technological signatures, which presents a significant challenge. We tend to look for signs that align with our preconceived notions of what technology should entail, such as radio signals, heat signatures, or geometric structures. But an advanced civilization, capable of constructing interstellar probes, might employ technologies so far beyond our comprehension that we would not identify them as artificial. Arthur C. Clarke famously stated that any sufficiently advanced technology is indistinguishable from magic, and this principle applies in reverse as well. If Atlas is the product of a civilization a million years more advanced than ours, it might appear entirely natural to our instruments. It could utilize propulsion systems that leave no discernible exhaust, communicate through undetectable means, or be constructed from materials that mimic natural rock and ice so perfectly that we would never suspect it was not a product of accidental geological processes. This is the predicament Loeb grapples with. How can one definitively identify something as technological when the full spectrum of possible technologies remains unknown? How can design be distinguished from coincidence when dealing with a single data point? His solution lies in identifying patterns, improbable yet functional occurrences. A trajectory that coincidentally passes near multiple planets could be random, but it also aligns perfectly with the objective of surveying those planets. A mass substantial enough to resist perturbations, but light enough to suggest a hollow structure might be natural. But it also aligns with the expectations of an engineered shell. A surface layer of carbon dioxide ice could form naturally, but it also represents a logical choice for thermal protection. Individually, none of these factors provide definitive proof, but they are suggestive. They are sufficient to prompt the inquiry, and Loeb's frustration, which is palpable in the interview, stems from the reluctance of much of the scientific community to even entertain the question. They prefer to assume Atlas is natural, categorize it as an interesting but ultimately ordinary comet, and move on. He describes this resistance, this gatekeeping, as he terms it, noting that mainstream science often reacts with hostility to ideas that challenge established narratives. The prevailing narrative currently posits that interstellar objects are natural debris, ejected from other star systems during planetary formation. Any suggestion that they might be something else, particularly technological, is typically dismissed as pseudoscience or a bid for attention. Loeb counters that science should be guided by data, not by assumptions. If the data indicates something unusual, it warrants investigation. We should be curious and willing to consider hypotheses that may cause discomfort, as the alternative is intellectual stagnation, closing our minds to possibilities simply because they seem improbable. He points to historical precedents where unlikely notions ultimately prove true. Continental drift was initially dismissed as absurd until the evidence became overwhelming. The heliocentric model of the solar system was considered heretical until telescopic observations confirmed it. Black holes were once regarded as mere mathematical curiosities with no physical reality until their detection. The pattern is consistent. An individual proposes an idea contradicting conventional wisdom, the establishment rejects it, data accumulates, and eventually, the new idea gains acceptance, prompting retrospective wonder as to why it took so long to recognize the obvious. Loeb is wagering that extraterrestrial visitors, technological entities from other star systems, will follow a similar trajectory. Currently, the concept resides on the fringe. Most scientists consider it improbable or impossible. However, as we discover more interstellar objects, scrutinize them more rigorously, and witness the accumulation of anomalies, the evidence will eventually become undeniable. At that juncture, Loeb desires to be recognized as someone who took the possibility seriously from the outset. Chapter 6. The mass budget is inconsistent. Let us revisit the numerical data, as this is where Loeb's argument becomes most tangible. The calculation of 33 billion tons is not merely an interesting observation, it imposes a constraint. It reveals fundamental information about Atlas's composition, structure, and the plausibility of its existence given our understanding of interstellar space. When Loeb discusses the mass budget in his interview, he refers to a relatively straightforward calculation: the estimated quantity of rocky material present in interstellar space and the expected frequency of encountering objects of various sizes passing through our solar system based on that quantity. The galaxy contains a finite amount of heavy elements such as carbon, silicon, iron, and oxygen, the fundamental components of rocks, planets, and asteroids. The majority of this material is contained within stars and planets. A portion drifts through interstellar space as dust and minute particles. Occasionally, some of this material is ejected from star systems during planetary formation, propelled by gravitational interactions with massive planets, thereby becoming interstellar debris. By aggregating all ejected material and distributing it across the vast volume of the galaxy, we can ascertain a density, a certain number of tons of rock per cubic light-year. This is a relatively small figure, given the immense size of space and its predominantly empty nature. However, we can estimate this density based on models of planet formation and observations of young star systems. Once this density is established, it becomes possible to calculate the anticipated frequency with which an object of a particular size should traverse our solar system. Small objects are common, leading to frequent sightings. Large objects, conversely, are rare, making their appearance almost unprecedented. This distribution follows a power law, allowing for the estimation of the expected rate for any size of interest. For Atlas, assuming an initial size estimate of 20 kilometers, Loeb calculated that an object of such magnitude should only be encountered approximately once every 10,000 years. Even with a revised estimate of 5 to 6 kilometers, based on the 33 billion ton mass, the frequency remains extremely low, perhaps once per 1,000 years, or even once every few thousand years, depending on the precise modeling of the interstellar population. Yet, we have detected it within a mere decade of active observation. This statistical anomaly is the point of tension Loeb consistently highlights. It is akin to predicting that a specific rare bird will fly past your window once a millennium and then observing it on your very first day of birdwatching. Is it simply a matter of extraordinary luck? Absolutely. Rare events do occur. People win the lottery and lightning strikes. However, when this statistical oddity is juxtaposed with all the other anomalies we have already discussed, the trajectory, the timing, the visual peculiarities, it begins to seem less like chance and more like something else entirely. There exists an alternative approach to resolving this enigma. It's conceivable that our current estimations of the interstellar material reservoir are imprecise. Perhaps there is a significantly greater abundance of rocky constituents dispersed throughout the cosmos than we presently acknowledge. If the density of celestial detritus were, say, 10 or even 100 times greater, then the discovery of Atlas early in our observational period would not be considered astonishing. However, this proposition introduces its own set of complexities. If interstellar expanses are densely populated with substantial celestial bodies, why have we not encountered more of them? The Vera Rubin Observatory, which commenced operations in 2025, is currently identifying asteroids at an extraordinary pace, detecting thousands each week within our own solar system alone. Were interstellar entities common, one would anticipate the Rubin Observatory to be registering them continuously. Yet, thus far, it has identified only a scant handful of potential candidates, the majority of which are still undergoing confirmation. Consequently, we face a dichotomy. Either the mass budget estimates are accurate, rendering Atlas a statistical anomaly, or those estimates are flawed, suggesting that interstellar objects are far more prevalent than previously understood. Regardless, a fundamental incongruity persists. Dr. Loeb leans towards a third possibility. Atlas, she posits, possesses an unusual mass not because it is a solid, dense rock, but rather because it is a constructed entity, a shell-like formation, possessing considerable volume but a low mass-to-volume ratio. This hypothesis would account for its estimated mass of 33 billion tons, sufficient to counteract the forces exerted by outgassing, yet not as substantial as a solid object of comparable dimensions would be. Consider the spacecraft we construct. The International Space Station, for instance, is colossal in size, yet its weight is comparatively negligible for its dimensions, being largely comprised of empty space and thin structural components. If viewed from a distance and presumed to be a solid metallic mass, its actual weight would be vastly underestimated. The same principle could apply to Atlas. If it is hollow, designed for minimal mass and maximum efficiency, it could plausibly possess the measured mass without being exceptionally rare. Nevertheless, this conjecture faces a significant obstacle. We lack direct empirical evidence to confirm Atlas's hollow nature. We are unable to examine its interior or ascertain its internal configuration. Our sole reliance is upon the trajectory data and the mass assessment derived from the absence of non-gravitational acceleration. These observations are, admittedly, consistent with a solid celestial body, albeit one of surprising mass. What is critically needed is a method to investigate its interior. Radar technology would be effective, provided we could achieve sufficient proximity. Radar possesses the capability to penetrate surfaces and reveal internal structures, a technique successfully employed to map the interiors of comets within our solar system by analyzing radio wave reflections. However, Atlas is presently too distant for terrestrial radar, and no suitably equipped spacecraft is in its vicinity. The high-resolution camera aboard the Mars Reconnaissance Orbiter, scheduled to photograph Atlas on October 3rd, is incapable of peering inside objects. It can only capture surface imagery. Nonetheless, it might yield valuable insights. Should Atlas exhibit an unconventional shape, an unnatural smoothness, or geometric regularity, or if it displays characteristics inconsistent with a naturally occurring comet, such observations would be meaningful, not conclusive, but certainly informative. Dr. Loeb expresses particular anticipation regarding the images from the high-resolution camera, especially concerning its ability to differentiate the nucleus from the surrounding coma. A common difficulty in observing comets stems from the luminous cloud of gas and dust that envelopes them, obscuring the solid core. It is akin to attempting to photograph a light bulb while someone is directing a flashlight into your eyes. The intense glare overwhelms any discernible detail. However, the high-resolution camera boasts exceptional resolution, designed to detect boulders on the Martian surface, objects measuring 1 or 2 meters across, from orbit. When directed at Atlas from a distance of 29 million kilometers, it should be capable of discerning features approximately 30 kilometers in size. While insufficient for resolving surface intricacies, this resolution is adequate to distinguish the central nucleus from the surrounding coma, thereby enabling a more precise size estimation. If the nucleus is determined to exceed 5 kilometers in diameter, and if the high-resolution camera confirms Atlas to be indeed 10, 15, or even 20 kilometers across, the mass budget dilemma intensifies. A solid object of such magnitude weighing only 33 billion tons would necessitate composition from an exceptionally lightweight substance, perhaps porous ice or a foamy material, a composition inconsistent with typical cometary makeup. In such a scenario, where Atlas appears both unusually large and unusually light, the technological hypothesis gains greater plausibility, not definitive proof, but certainly a stronger footing. Dr. Loeb briefly touches upon another element of the mass budget argument that warrants deeper exploration. The frequency of interstellar objects encountered should correlate with the prevalence of planetary systems undergoing formation and expelling debris. If planet formation is a common cosmic phenomenon, with most stars hosting planetary companions, then the rate of such ejected material should be relatively high. Conversely, if planet formation is infrequent, the rate should be correspondingly low. Current astronomical understanding, largely thanks to missions like Kepler and other exoplanet surveys, indicates that planets are indeed common, with the majority of stars possessing planetary systems. Consequently, mass budget calculations are predicated on a substantial rate of interstellar debris generation, envisioning billions of planetary systems expelling rocks and comets into interstellar space over cosmic timescales, thereby fostering a significant population of transient objects. However, if the majority of this debris consists of smaller entities, pebbles, boulders, and objects perhaps comparable in size to a football field, then larger specimens remain scarce, and Atlas continues to present as an outlier. Unless, as Dr. Loeb suggests, a portion of these interstellar objects are not natural in origin. If even 1% of them are artificial probes dispatched by civilizations engaged in galactic exploration, then the statistical landscape is fundamentally altered. A considerable mass budget of naturally ejected rocks is then unnecessary to account for a technological visitor. The mere existence of a single civilization within the Milky Way capable of dispatching probes to neighboring star systems suffices. Considering the sheer number of stars and the immense age of our galaxy, this prospect does not appear untenable. This is the juncture at which Dr. Loeb's reasoning converges with the broader inquiry into extraterrestrial intelligence. If we are indeed alone in the galaxy, if Earth is the sole planet to have ever developed a technologically advanced civilization, then every interstellar object we detect will invariably be a natural formation of rock and ice, nothing more. Conversely, if we are not unique, if intelligence is widespread, or even moderately uncommon but present, then some interstellar objects will undoubtedly be artificial in nature, probes, derelict vessels, or ancient spacecraft traversing the void. The critical question then becomes, how do we discern the artificial from the natural? How do we identify the manufactured among the background cosmic detritus? Dr. Loeb's proposed solution is a systematic approach. We must meticulously observe every interstellar object, diligently measure its properties, meticulously track its trajectory, and actively search for anomalies. When any characteristic deviates from the norm, be it mass, trajectory, or chemical composition, a thorough investigation is warranted. To overlook a genuine technological visitor would represent one of humanity's most profound errors. Atlas, with its 33 billion-ton mass and its array of peculiar attributes, exemplifies precisely the sort of object demanding such rigorous scrutiny. It is neither unequivocally natural nor clearly technological. It resides within an ambiguous gray zone, leaving us uncertain in either assessment. This very uncertainty, Dr. Loeb contends, constitutes sufficient justification for its close and continuous observation. Chapter 7. Approaching the Sun, October 29th. This date is pivotal. It marks the moment Atlas reaches perihelion, its closest approach to the Sun, and consequently vanishes from our view behind that star. According to Dr. Loeb, this is not merely an inconvenient observational hiatus, but potentially the most crucial juncture in the entire encounter. When an object attains perihelion, it is at its orbital point of greatest proximity to the Sun, experiencing its strongest gravitational influence. Its velocity is at its peak, and the curvature of its trajectory is most acute. It is at this precise moment that significant alterations to its orbital path, deceleration, acceleration, or changes in direction, are most effectively executed. A minimal application of thrust yields the most substantial deviation in trajectory, a principle known as the Oberth effect. This is a foundational tenet of orbital mechanics universally understood by spacecraft designers. Typically, the Oberth effect is employed to increase velocity. Engines are ignited when an object is traveling at its highest speed, in close proximity to a massive celestial body such as the Sun or a planet, as the added kinetic energy exerts the greatest impact. Pioneer, Voyager, and indeed every probe dispatched to the outer solar system has utilized gravitational assists and meticulously timed engine firings at perihelion to augment speed and reach their destinations. However, the effect operates in reverse as well. It can be utilized to reduce velocity, to brake, to dissipate momentum, thereby allowing gravity to ensnare an object into a bound orbit rather than permitting it to follow an escape trajectory. This maneuver is termed a reverse Oberth maneuver and is precisely what one would employ to transition from a transient passage through a star system to permanent residency within it. Currently, Atlas is traversing a hyperbolic trajectory, indicating a velocity exceeding escape velocity. It is poised to swing around the Sun and then re-enter interstellar space. This course will persist unless some intervention occurs, unless it decelerates at perihelion. The timing of this event is remarkably precise. On October 29th, the very day Atlas reaches perihelion, Earth will be situated on the diametrically opposite side of the Sun. We will be experiencing what is known as solar conjunction, with the Sun positioned directly between Earth and Atlas, its overwhelming brilliance obscuring any observational capabilities. Ground-based telescopes will be rendered ineffectual. Even space-based observatories like the Hubble and James Webb telescopes, which are unaffected by daylight, will encounter significant challenges due to the Sun's corona and luminosity, making imaging of any object in close proximity to the solar disk virtually impossible. Dr. Loeb characterizes this as a concealed vantage point. If one were devising a trajectory to facilitate an unobserved course correction, this scenario would be ideal. Arriving at perihelion, when the planet possessing the most advanced telescopic capabilities and the keenest interest in tracking your progress is positioned on the far side of the star, enabling the maneuver to be executed while unobserved. Is this a deliberate act? Is it intentional? Or is it merely another coincidence in a series of improbable occurrences? If one were to slightly alter Atlas's trajectory, shifting its arrival at perihelion by a few days or weeks, the statistical likelihood of Earth being on the opposite side of the Sun at that precise moment is low, though not impossible. Estimates suggest a probability ranging from 1 in 20, depending on the calculation methodology. This adds another improbable event to an already extensive list. However, what lends this particular circumstance significant weight is the consequence. If Atlas executes a maneuver on October 29th, if it engages its propulsion system to decelerate and enter orbit around the Sun, we will not ascertain this fact immediately. We will only discover it weeks later, upon its reappearance from behind the Sun in late November or early December, when we recalculate its trajectory. At that juncture, if its orbit has indeed changed, if Atlas is no longer on an escape path, but rather on an elliptical trajectory that confines it within the solar system, we will know that an event has transpired. We will confirm that a maneuver occurred, though the precise timing, method, or nature of the propulsion system employed will remain unknown. All we will possess is the before and after, the trajectory upon arrival and the trajectory upon departure. Dr. Loeb calculates that if Atlas successfully captures itself into orbit, transitioning from a hyperbolic to an elliptical path, it could then proceed towards Earth with considerable rapidity. The projected timeline for its closest approach to our planet is late November to early December. This proximity would not be in the sense of a collision. Atlas would still be millions of kilometers distant, but close enough to afford us a significantly clearer view than is currently possible. This, in turn, raises questions of intent. If Atlas is indeed technological, a probe or spacecraft of some designation, what would be its objective? What would be the purpose of remaining within the solar system rather than simply continuing its transit? One plausible explanation is observation. A probe designed to study inhabited worlds would logically seek to linger in proximity. It would aim to orbit at a distance conducive to monitoring radio transmissions, detecting industrial signatures, and tracking the movements of spacecraft and satellites. Such a mission would aim to accumulate data over months or even years, thereby constructing a comprehensive profile of the civilization it encounters. Another conceivable purpose is resource acquisition. The solar system is replete with valuable materials, including water ice found on comets and moons, metallic asteroids, and helium-3 present in the atmospheres of gas giants. An advanced civilization might dispatch probes to inventory stellar system resources and identify potential targets for future exploitation. Alternatively, the purpose could be defensive. A probe detecting signs of technological civilization, evidence of intelligent life, might be programmed to neutralize it preemptively before it poses a threat. This aligns with the dark forest hypothesis that Dr. Lowe alludes to, the notion that revealing one's existence to other civilizations is inherently perilous due to the uncertainty of their intentions. Consequently, the most prudent strategy might involve preemptively destroying any emergent intelligence encountered before it attains the capacity to pose a threat. This represents a grim calculus, but not an irrational one. Dr. Lowe does not advocate for this scenario. She is not asserting that Atlas constitutes a weapon or that we face immediate peril. However, she emphasizes that if we detect a technological entity, we must thoroughly evaluate all potential implications, including hostile ones. We cannot afford to presume benign intentions. The encouraging aspect, if such a term is applicable, is that we may receive some advance notice. Should Atlas remain within the solar system, capture into orbit, and initiate maneuvers toward Earth, its approach will be discernible. We would have weeks or months to observe it, attempt communication, and endeavor to comprehend its objectives. This scenario contrasts sharply with an unexpected arrival, leaving no time for reaction. However, the observational window is restricted. From its reappearance in late November until its closest approach to Earth in late December, we have approximately 4 to 6 weeks. During this critical period, continuous observation is paramount. Every telescope, every spacecraft, every sensor at our disposal must be directed towards it. Dr. Lowe notes in her interview that NASA's Juno probe, currently in orbit around Jupiter, might be capable of observing Atlas during its close pass by Jupiter in March of 2026. The European Space Agency's JUICE spacecraft is scheduled for observations in November, and Mars orbiters will be tracking it in early October. These assets should be coordinated, their data integrated, ensuring no crucial information is missed. For if October 29th represents the moment of fundamental change, the instant Atlas decides to remain, then we must be prepared for the subsequent developments. And, at present, we are not. We lack a comprehensive plan. There is no designated organization responsible for managing such a scenario. We have not even achieved a consensus regarding the level of concern we should entertain. Dr. Lowe's palpable frustration with this lack of preparedness is evident in her interview. She persistently underscores the necessity of approaching this situation with utmost seriousness. Even if the probability is low, even if there is only a 1% chance that Atlas is technological, the potential ramifications are so profound that it warrants prioritization. We ought to be mobilizing resources and initiating discussions at the highest governmental echelons concerning the appropriate response should an interstellar visitor prove to be more than merely a celestial rock. Nevertheless, the response from much of the scientific community has been largely dismissive, with some labeling her ideas as preposterous and others accusing her of seeking attention. Many argue that even contemplating the possibility of alien technology undermines the credibility of serious astronomical research. Dr. Lowe's counterargument, however, is straightforward. Scientific inquiry must be guided by evidence, not by preconceived notions. The evidence pertaining to Atlas, while not definitively conclusive, is sufficiently anomalous to warrant investigation. Its trajectory is peculiar, its mass exceeds expectations, its timing appears conveniently synchronized, and its visual characteristics present irregularities. Each of these factors, in isolation, might be readily explained. However, when considered collectively, they form a pattern that merits serious attention. The pivotal moment of October 29th, the perihelion passage obscured by the sun, is when we are likely to begin obtaining answers. If Atlas reappears in late November on the same escape trajectory it followed upon arrival, it is probable that it is simply a comet, an unusual one, to be sure, but ultimately a natural phenomenon. In such a case, we can all collectively exhale in relief. However, should it emerge on a different trajectory, if its orbit has been altered, indicating it is no longer on a path of departure, then we will know that something extraordinary has transpired. At that point, the question of whether Atlas is natural or technological will assume a far greater urgency. Chapter 8. Preparing for all possibilities. Dr. Lowe makes a point in her interview that is easily overlooked but fundamentally critical. She states, "It could come to save us or to destroy us. We'd better be prepared for both possibilities and verify that all interstellar objects are just rocks." This statement encapsulates her overarching philosophy on how we should approach interstellar visitors, not with unbridled optimism, nor with paralyzing fear, but with meticulous, systematic observation and a willingness to entertain the entire spectrum of potential outcomes. The Savor scenario represents the popular conception of first contact. It is envisioned that an advanced civilization, having mastered interstellar travel, would have necessarily overcome the existential challenges that plague nascent species, such as resource scarcity, environmental degradation, and self-destructive conflicts. Such civilizations would presumably exist in a state of post-scarcity and post-violence, exhibiting enlightenment far beyond our current comprehension. In this optimistic vision, they might impart their knowledge to us, offering advancements in technology, medicine, and solutions to our current predicaments. This aligns with the idealistic notion of Star Trek-esque diplomacy, fostering peaceful exchanges of ideas between species. And this scenario is not without its plausibility. If intelligence is a widespread cosmic phenomenon, and if technologically advanced civilizations arise with regularity, it stands to reason that at least some of them would develop along benevolent trajectories. They would transcend their destructive impulses, establish stable and peaceful societies, and extend offers of assistance to younger civilizations rather than posing threats. However, the destroyer scenario, from a specific perspective, is equally conceivable. This is where the dark forest hypothesis comes into play, though Dr. Loeb carefully avoids dwelling on it excessively in her interview. The fundamental premise is as follows. The universe possesses finite resources, stars, planets, raw materials, and energy. If intelligent life is prevalent, then competition for these resources becomes inevitable. When encountering another civilization, one faces an inherent dilemma. Their intentions remain unknown. It is impossible to ascertain whether they are peaceful or aggressive, whether they will compete for resources or seek to eliminate you preemptively. In such circumstances, the most secure course of action might be to strike first, to annihilate any emergent civilization detected before it attains the capacity to pose a threat. This action would not stem from malice, but from a rational calculation of self-preservation. It is a grim calculus, yet it is not irrational. Dr. Loeb does not endorse this scenario. She is not suggesting it is her expectation. However, she maintains that it cannot be definitively ruled out. If Atlas is indeed a technological artifact, we lack knowledge of its creators or the directives it is programmed to follow. It could be a benevolent explorer or something far more menacing. This underscores her emphasis on preparedness. We must be equipped to address both eventualities. We require established protocols for communication should the visitor prove amicable, and for defense should it prove hostile. The challenge lies in our current state of unpreparedness for either scenario. We have no universally accepted method for transmitting messages to an extraterrestrial intelligence, nor a global consensus on what to communicate or who would speak on behalf of humanity. Furthermore, we certainly possess no means of defending against an advanced technological threat should one materialize. Our most formidable weaponry, nuclear missiles, would likely prove ineffective against an object the size of Atlas. Even if interception were feasible, which it is not at its current velocity, destroying a 20-kilometer object would merely generate thousands of smaller fragments, still on a collision course, exacerbating the problem rather than resolving it. Moreover, if Atlas possesses propulsion capabilities and can maneuver, targeting it becomes even more complex. An evasive moving target presents an almost insurmountable challenge for our current arsenal. We'd require advanced capabilities beyond our present reach, perhaps directed energy systems like high-intensity lasers or particle beams. These would deliver energy at the speed of light, leaving no opportunity for evasion. However, such technology is not at our disposal, not to the magnitude necessary for a substantial celestial body, nor with the required power output. At the very least, we are decades away from such a technological threshold, possibly centuries. Therefore, should Atlas prove to be adversarial, our recourse is severely restricted. We might attempt communication, seeking dialogue and attempting to persuade its controllers that we pose no danger. Yet, if these efforts prove fruitless, our options are exhausted. This is precisely why Loeb advocates so fervently for the establishment of a global organization to manage these extraordinary circumstances. The critical decisions and potential actions demanded by such scenarios cannot be left to individual nations acting in isolation. They necessitate unified direction and a coordinated global response. He draws parallels to other universal concerns. Environmental shifts, for instance, demand international collaboration as emissions from one nation impact the entire planet. The spread of nuclear arms requires treaties and oversight, as a single rogue state armed with such weapons poses a threat to all. Similarly, pandemics necessitate synchronized public health strategies because disease knows no geographical boundaries. An extraterrestrial visitor, regardless of its intentions, presents an even more profound challenge. It transcends human or national concerns, becoming a planetary issue demanding a planetary solution. Unfortunately, we currently lack the institutional framework to address this. While the United Nations has established committees for space exploration and planetary defense, their focus remains on asteroids and orbital debris, not interstellar visitors. There is no entity specifically assigned to detect technological signatures or to orchestrate responses to potential contact events. Loeb proposes a fundamental shift. We require an organization vested with the authority and resources to track extraterrestrial objects, analyze them for evidence of artificial origins, and formulate response strategies. This body should be international, comprising representatives from leading spacefaring nations and incorporating insights from the scientific community. Crucially, it must possess clear operational guidelines and decision-making frameworks, a sequence of actions to follow upon detecting a specific signature or observing particular behaviors, escalating response levels accordingly. Without such established protocols, we are navigating blind, improvising as we go. And when confronting a situation as potentially momentous as first contact with an alien intelligence, improvisation is a recipe for catastrophe. Loeb also emphasizes the necessity of verification. He asserts that we must confirm that all interstellar objects are indeed natural phenomena, rather than merely assuming so. This entails rigorous observation, precise measurement of their characteristics, and vigilant scrutiny for anomalies. When unusual findings emerge, they must be thoroughly investigated rather than summarily dismissed. This is where his proposed low scale becomes relevant. Each interstellar object would be assigned a rating from 0 to 10 based on the number of peculiar features it exhibits. Any object scoring above 5 would trigger a synchronized international observation campaign, deploying all available telescopes and spacecraft in the vicinity for maximum effort in characterizing the object and determining its nature. For Atlas, such a campaign should already be in progress, with numerous telescopes tracking it and coordinated observations from Mars orbiters, JUICE, and Juno. As it approaches, real-time data analysis should be underway, seeking any indication that Atlas is behaving in ways inconsistent with natural objects. Yet, according to Loeb's account, this is not occurring. While individual research teams are indeed observing Atlas using instruments like the Hubble and Webb telescopes and ground-based observatories, there is no cohesive campaign, no central coordination, and no systematic endeavor to ascertain Atlas's true identity. A significant contributing factor is the prevailing belief among most astronomers that Atlas is simply a comet. The presence of a coma, a tail, and outgassing leads them to conclude its natural origin. With this conclusion reached, the impetus for further observation diminishes and attention shifts to other celestial phenomena. However, Loeb contends that this conclusion is premature. While Atlas exhibits cometary traits, it also possesses characteristics that do not entirely align, such as its trajectory, mass, timing, and chemical composition. These anomalies do not vanish with the observation of a tail. They persist and demand an explanation. Until we can account for all these peculiar aspects through natural processes, the investigation should remain open. We must continue observing, measuring, and questioning as the cost of error. Dismissing a genuine technological visitor as merely another comet is immeasurable. We would forfeit the opportunity to learn from an advanced civilization, to establish contact, and to receive warnings if the visitor were hostile. Loeb's palpable frustration is evident when discussing this, feeling as though he is speaking into a void, warning of a possibility no one is willing to seriously consider. He recognizes that if he is correct, and Atlas is indeed more than a mere celestial body, future generations will question why a more thorough investigation was not conducted when the opportunity arose. Chapter 9. The Scientific Backlash. It is imperative to address the counterarguments, as Loeb's assertions have generated significant reactions within the astronomical community, much of it critical, and at times, exceptionally so. Tom Statler of NASA, who serves as the program scientist for small bodies within the AWIS framework, has been a prominent voice of dissent. He has consistently maintained that all available data indicates Atlas is a natural comet. The variations in brightness, the presence of a tail, and the outgassing are all consistent with an icy body warming as it approaches the sun. There is nothing in the observations that necessitates the invocation of extraterrestrial technology. Statler highlights the inherent unpredictability of comets, noting that even those within our solar system can exhibit behaviors that appear anomalous until their underlying physics is understood. They fluctuate in brightness as different patches of ice sublimate, develop jets that alter their trajectories unexpectedly, and can fragment and reform. These are complex and dynamic objects, and Atlas fits this profile perfectly. The initial brightness, which led to the early estimation of its size at 20 kilometers, can be attributed to the formation of a large coma far from the Sun. If Atlas is particularly rich in volatile compounds, substances that sublimate at low temperatures, it could commence outgassing earlier than typical comets, generating a bright cloud of gas and dust that exaggerates its apparent size. The alignment of its trajectory with the ecliptic plane, a purported 1 in 500 coincidence, may not be as extraordinary as it seems when accounting for observational bias. We are more likely to detect objects traversing the inner solar system near the plane of planetary orbits because that is where most of our telescopes are directed. Objects approaching at steep angles, perpendicular to the ecliptic, might pass through the solar system undetected. The frequent close approaches to multiple planets could also be a result of selection bias. We tend to notice and document interstellar objects that pass near planets because these encounters are inherently interesting, prompting scientific papers and focused observation. Objects that do not pass near any notable celestial bodies might go unobserved or unremarked. Chris Lintott from Oxford University has expressed his criticism even more directly, describing Loeb's hypothesis of alien technology as absolute nonsense. He argues that resorting to exotic explanations for phenomena with clear natural interpretations constitutes poor scientific practice. It is, he contends, the modern equivalent of seeing lights in the sky and immediately assuming they are aircraft, rather than considering more mundane explanations like terrestrial aircraft, satellites, or atmospheric phenomena. Lint and others have pointed out that this is not the first time Loeb has posited that interstellar objects are indicative of alien technology. He made a similar claim regarding oumuamua in 2017, suggesting its unusual acceleration could be explained by a light sail, a thin, reflective sheet propelled by solar radiation. This assertion was met with widespread criticism from other astronomers who demonstrated that natural outgassing could equally account for the observed acceleration. The critics observe a pattern. Loeb tends to interpret any interstellar object with slightly unusual characteristics as evidence of alien origin. This, they argue, is sensationalism, an attempt to garner attention, and it undermines the credibility of legitimate research into extraterrestrial intelligence. Scientists involved in the search for extraterrestrial intelligence, SETI, have expressed particular frustration. Organizations like the SETI Institute are dedicated to finding evidence of alien civilizations through the use of radio telescopes to detect signals from other star systems. They approach this search with seriousness, adhering to stringent protocols and exercising caution before making claims without substantial evidence. Then, Loeb emerges, declaring that every peculiar space rock might be an alien probe, thus potentially casting the entire field in a less credible light. Skeptics of SETI, those who view the search for aliens as a wasteful endeavor, cite Loeb's claims as proof that the entire enterprise is pseudoscience. The frustration within the SETI community stems from their commitment to meticulous, systematic scientific investigation, which Loeb's high-profile speculations complicate. It becomes easier for critics to dismiss their work, for funding agencies to reduce their budgets, and for the public to conflate legitimate research with conspiracy theories about UFOs and ancient astronauts. Loeb's response to this criticism remains consistent. He argues that science should be guided by data, not by concerns about reputation or public perception. If the available data suggests something unusual, it warrants investigation, even if the hypothesis is uncomfortable or challenges our preconceived notions of probability or possibility. He points to the history of science, which is replete with instances where the prevailing consensus was incorrect. For decades, continental drift was dismissed as impossible before the evidence became overwhelming. The idea that bacteria could cause ulcers was ridiculed until its validity was established. Black holes were once considered mere mathematical curiosities with no potential for detection. In each of these cases, individuals proposing unconventional ideas faced criticism and mockery, with claims that they were damaging their respective fields. Ultimately, they proved to be correct, not due to superior intellect, but because they prioritized data over consensus. Loeb perceives himself as part of this scientific tradition. He does not assert certainty. He does not definitively state that Atlas is alien technology. Instead, he posits that its anomalous characteristics warrant careful investigation, and that dismissing the possibility solely due to its perceived unlikelihood would be a mistake. He also presents a pragmatic argument. Even if the probability of Atlas being technological is as low as 1%, the implications are so profound that it deserves serious consideration. If we are mistaken and dismiss it as a comet, missing a genuine encounter with alien intelligence, It is an error from which humanity can never recover. The object will depart, the opportunity will be lost, and humanity will spend eternity pondering what was missed. Conversely, if we investigate thoroughly and conclude it is natural, we lose little beyond some telescope time and research effort. The cost of a false positive, investigating a natural object as potentially technological, is minimal. However, the cost of a false negative, overlooking a technological object by assuming it is natural, is immense. This disparity, Loeb argues, should prompt a shift in our approach. We should lean towards investigation, meticulously examining every interstellar visitor, particularly those exhibiting unusual traits, and only conclude they are natural after all alternative explanations have been systematically ruled out. However, the mainstream scientific community does not share this perspective. They perceive resources as finite, telescope time as precious, and they are unwilling to expend either on speculative ventures. If an object exhibits the characteristics of a comet, behaves like a comet, and possesses a straightforward natural explanation for its properties, then it is classified as a comet, and attention moves elsewhere. The core of this debate lies in divergent philosophies of scientific inquiry. Should we adopt a conservative stance, adhering to established explanations until definitively disproven? Or should we embrace an exploratory approach, considering unconventional possibilities even when conventional ones are available? Loeb firmly resides in the exploratory camp. He would rather investigate 100 natural objects under the assumption they might be technological and find nothing, than miss a single genuine technological object by dismissing it prematurely. His critics, on the other hand, are more conservative, demanding compelling evidence before entertaining extraordinary hypotheses. To be fair, the critics have a valid point. The assertion that an interstellar object is alien technology is an extraordinary claim. It would fundamentally alter our understanding of the prevalence of intelligence in the universe, confirm that humanity is not alone, and raise profound questions about the intentions and capabilities of its creators. Extraordinary claims necessitate extraordinary evidence. As of now, the evidence suggesting Atlas is technological is, at best, suggestive, not extraordinary. Its trajectory is unusual, but not impossible. Its mass is significant, but not inconsistent with a dense comet. Its visual characteristics are peculiar, but explicable. Its chemistry is unconventional, but falls within the range of natural variation. Nothing about Atlas definitively points to an artificial origin. Therefore, the critics argue, we should opt for the simpler explanation. It is a comet originating from another star system. An intriguing one, certainly worthy of study, but ultimately just a natural object governed by natural laws, requiring no extraterrestrial explanation. This leaves us in a state of uncertainty. The available data is inconclusive in either direction. Atlas could be natural, or it could be technological. We lack sufficient information to make a definitive determination. This uncertainty is precisely why Loeb persists in advocating for further observations, measurements, and rigorous study. The only path to resolving this question is by acquiring more robust data. Chapter 10. What happens next? Here we are. It is the beginning of October. Atlas remains visible in the night sky, though its visibility is diminishing as it approaches the sun and solar glare intensifies. Over the next 4 weeks, we will receive answers to many of the questions that have accumulated throughout this narrative. October 3rd marks the first significant milestone. On this date, Atlas will achieve its closest approach to Mars, passing within 29 million kilometers of the red planet. NASA's Mars Reconnaissance Orbiter will be prepared, its high-resolution imaging science experiment, HiRISE, camera directed towards the interstellar visitor. The resolution should be sufficient to distinguish the nucleus from the surrounding coma, providing our clearest view yet of Atlas's core structure. If HiRISE reveals a nucleus exceeding 5 kilometers in diameter, confirming Atlas is approaching 10 or 15 kilometers in size, this would bolster Loeb's argument regarding the mass-budget discrepancy. A large, relatively lightweight object that resists perturbations from outgassing would appear less like a natural comet and more like an object with an engineered structure. Conversely, if the nucleus is small, measuring only a few kilometers or less, the estimated mass of 33 billion tons might require revision. It is possible the method used for its calculation contains systematic errors, or that the outgassing is more asymmetrical than anticipated, creating thrust forces that cancel each other out in ways we are not accounting for. A smaller nucleus would relegate Atlas back towards the category of a natural comet. Mars Express and ExoMars Trace Gas Orbiter, both operated by the European Space Agency, ESA, will also observe Atlas during its Mars flyby. They will employ spectrometers to analyze the composition of the coma, searching for molecules that might shed light on Atlas's formation location and composition. More carbon dioxide, more cyanide, or something entirely unexpected. Every measurement contributes to a more comprehensive understanding. Furthermore, there exists a remote, yet plausible possibility that Atlas might deploy a component during the Mars encounter, perhaps a smaller probe or a lander, something that detaches from the main body and alters its course towards Mars. Loeb has calculated that the required ejection velocity would not be substantial, merely a few kilometers per second. From Earth, we would likely not detect such an object due to its size and faintness, but Mars orbiters might register it, particularly if it exhibits active maneuvering. Is this scenario probable? Almost certainly not. However, it is the type of event we must remain vigilant for, because if it occurs, if something separates from Atlas and heads towards Mars, it would be a game changer, providing irrefutable evidence of technology beyond any natural explanation. Following its encounter with Mars, Atlas will continue its inward trajectory. Throughout October, it will draw progressively closer to the Sun, increasing in brightness in the sky, but also becoming more challenging to observe due to the intensifying solar glare. Ground-based telescopes will lose sight of it by mid-October. Space telescopes might maintain observation for a longer period, but even they will struggle as Atlas approaches within a few degrees of the Sun from our perspective. Then, October 29th will arrive. Perihelion, the moment of critical significance. Atlas will reach its closest point to the Sun, approximately 1.4 astronomical units, just inside the orbit of Mars. At this point, it will be on the opposite side of the Sun from Earth, rendering it obscured and unobservable. If Atlas is programmed to execute a maneuver, this would be the opportune time. This represents the optimal moment for a reverse orbital burn. By leveraging the Sun's gravitational influence to amplify the effect of any propulsion system, a relatively minor alteration in velocity at perihelion could be sufficient to transition from a hyperbolic escape trajectory to an elliptical bound orbit. We will not witness this event directly, nor will we detect the maneuver in real time. We will only learn of it retrospectively, after Atlas reemerges from behind the Sun in late November, when its orbit is recalculated. If its trajectory has changed, if it is no longer on an escape path, this will indicate that something significant has transpired. November heralds a new phase of observations. ESA's JUICE spacecraft, currently en route to Jupiter but still relatively proximate to the Sun, will have one of the most advantageous vantage points to observe Atlas as it emerges from solar conjunction. JUICE will utilize multiple instruments, including cameras, spectrometers, and particle detectors, for its observations. The data will not be transmitted immediately, as JUICE is distant from Earth and employing a low-bandwidth antenna. However, eventually, likely by February 2026, we will receive detailed measurements from this period. If Atlas exhibits heightened activity after perihelion, such as significant outgassing or unusual brightness fluctuations, JUICE may capture these phenomena. And if any signs of artificial activity, any anomalies inexplicable by natural cometary processes, emerge, this is where they would likely be detected. In late November and early December, Atlas will make its closest approach to Earth. This is not close in the sense of a near miss. We are referring to a distance of 1.8 astronomical units, approximately 170 million miles. However, it will be close enough for our most advanced telescopes to achieve excellent observational clarity. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories equipped with adaptive optics will all be trained on Atlas, capturing data across multiple wavelengths. This period presents our best opportunity to fully characterize the object, to measure its rotational rate, its shape, and its composition in detail, searching for anything unusual, anything that deviates from the established comet model. Subsequently, Atlas will continue its journey, passing Earth and proceeding outwards towards the orbit of Jupiter. In March of the year 2026, NASA's Juno probe will have the opportunity to examine it as it makes a close pass by Jupiter. This represents another opening for detailed, near-field measurements, another prospect to capture something we might have overlooked previously. Following this, Atlas will either depart from our solar system, continuing its hyperbolic course out into the vastness of interstellar space, or it will remain, following a solar orbit dictated by the path it established at its closest approach to the Sun. Should it depart, we will observe its gradual dimming into the distance, eventually becoming too faint to follow, and we will then add it to the roster of interstellar visitors. An object of great fascination that prompted intriguing inquiries, but which ultimately proved to be a natural phenomenon. If, however, it remains, the entire situation transforms. An object originating from outside our solar system that has either intentionally or unintentionally become a permanent resident within our celestial neighborhood becomes an enduring fixture. It becomes something we can scrutinize for years or even decades. It becomes something to which we could potentially dispatch spacecraft for exploration and something that might, just might, offer a response if we attempt to establish contact. Loeb's consistent message throughout this entire discourse, and indeed through all his published works concerning Atlas, is that we must be prepared for either eventual outcome. We must observe with keen attention. We must collect high-quality data. We must be ready to react if the object is revealed to be more than merely a celestial rock, for this is merely the prelude. The Vera Rubin Observatory is now fully operational, diligently surveying the heavens with unparalleled effectiveness. It is discovering new asteroids by the thousands. And among these burgeoning discoveries, we are expected to find additional interstellar objects, perhaps one every few months, or potentially more frequently if they are indeed common. Each such discovery will present an opportunity, a chance to study material originating from another star system, a chance to gain insights into the processes of planet formation in different galactic regions, and perhaps, just perhaps, a chance to encounter something that was not at all a product of natural processes. Loeb advocates for a methodical approach, for rating each interstellar object according to his established scale, for thoroughly investigating those that exhibit peculiarities, and for refraining from dismissing possibilities simply because they seem improbable. This is because the cosmos is replete with unexpected occurrences, and the most significant error we could make would be to cease our observations under the assumption that we already comprehend what we are likely to find. Atlas serves as a preliminary test case. It is the third interstellar visitor we have identified, and by far the most debated. The discussions surrounding it, the disagreements between Loeb and his detractors, are shaping the approach we will adopt for future discoveries. Will our stance be one of conservatism, adhering to natural explanations unless compelled to consider alternatives? Or will we adopt an exploratory posture, investigating diligently and maintaining an open mind? The resolution of this particular question holds significance because it will dictate our perceptions. If we presuppose that everything is natural, we will interpret every observation through that prejudiced lens, and we will consequently overlook indications of technology, even if they are present. Conversely, if we are overly eager to perceive extraterrestrial intelligence everywhere, we will squander resources pursuing unfounded leads and damage our credibility. Striking this balance is a challenge. It demands sound judgment. It necessitates following the evidence rather than our preconceived notions. And it requires humility, acknowledging that our knowledge is incomplete and that the universe may present us with surprises we have not yet envisioned. Whatever Atlas ultimately proves to be, whether it is a comet or something more extraordinary, it has already imparted a valuable lesson. It has demonstrated that interstellar visitors are not merely theoretical curiosities. They are tangible objects that we are capable of detecting and examining. Furthermore, some of them exhibit characteristics sufficiently unusual to prompt us to reevaluate our fundamental assumptions. This process of questioning, this readiness to scrutinize anomalies rather than dismiss them, is precisely what the scientific endeavor is intended to be. It is not about a blind acceptance of unconventional notions, nor is it about a knee-jerk rejection of them. Rather, it is about meticulous observation, precise measurements, and an honest appraisal of what the data reveals. The ensuing months will be pivotal. October 3rd, October 29th, the latter part of November, and the early days of December. Each of these intervals will bring forth new data, fresh observations, and additional fragments of the overall puzzle, and by the close of the year, we will possess a considerably clearer understanding of what 3 Atlas truly represents. Until then, we watch, we anticipate, and we ponder. This has been an exploration into one of the most captivating objects ever detected within our solar system, an interstellar visitor that challenges our comprehension and extends the limits of what we believe to be achievable. Whether Avi's hypothesis is ultimately validated or whether Atlas is ultimately identified as an unusual but naturally occurring comet, the questions it provokes are profound. We have examined the trajectory analysis, the statistical improbabilities, the mass computations, the visual discrepancies, and the chemical enigmas. We have heard Loeb's arguments and the counter-arguments from his critics. We have delved into the implications if Atlas were indeed of technological origin and what our course of action should be. The narrative of Atlas is still unfolding. October 29th is approaching. And when that day arrives, when Atlas recedes behind the sun and either remains with us or departs, we will gain a little more insight into our position within the cosmos. Thank you for dedicating this time to exploring this mystery alongside me. If you found this in-depth examination beneficial, I would be grateful if you would click the like button and subscribe for more content of this nature. The universe is brimming with enigmas, and we are only just beginning to uncover them. Before I conclude, I should emphasize that all assertions discussed herein are grounded in publicly accessible data and published research. The interpretation of this data, particularly Loeb's hypothesis concerning potential technological origins, remains a subject of considerable debate within the scientific community. The prevailing belief among most astronomers is that Atlas is a natural comet, and this remains the most probable explanation. However, the anomalies are concrete, the questions are valid, and the discussion is certainly worthwhile. Maintain your curiosity, continue to gaze upwards, and remember that the universe has surprised us in the past and will undoubtedly surprise us again. Good night.